Mass in contrast to weight. One of the most widespread confusions in everyday language is treating mass and weight as though they were the same concept. Yet in physics they refer to quite different realities. On the one hand, there is mass, which describes the amount of matter that makes up an object or a living being, and which essentially remains unchanged regardless of where in the universe one may be. On the other hand, weight is the force that gravity exerts on that mass, and it will vary depending on the strength of the gravitational field at each location. To picture this in a simple way, let us imagine a person here on Earth standing on a scale. The number they see on that device is commonly called their weight. However, if we transported this same individual with that same scale to the moon, they would see the reading decrease substantially, maybe to 1/6 of what it was on Earth. Even so, no one would claim that this person now has less substance in their body. They continue to have the same arrangement of atoms, the same biological composition. Consequently, their mass remains unchanged, while their weight, the gravitational force acting on them in that place, does indeed change. Now, why does this get so easily confused? To a large extent, it is because the majority of people step on a bathroom scale and see a number expressed in kilograms, which they call my weight. From a physics perspective, that scale is in fact measuring the force exerted by the Earth upon us, or more accurately, the force with which the Earth pulls us downward and how the scale responds to that. Something that would be different on another planet with a different gravitational pull. Our mass would not vary, yet the scale's reading would, because the local gravitational force is not the same everywhere. This distinction is particularly useful in many contexts. For example, if we think of traveling to places beyond Earth, designing satellites, or simply explaining why in an elevator one may feel heavier or lighter for a moment. Depending on the acceleration in the cabin, the key is being precise about mass as the amount of matter and weight as the measure of the pull from the environment. A single kilogram of mass remains the same whether you are on Earth, on Mars, or in interplanetary space, while weight, as a force, depends on the gravitational circumstances of each spot. In more practical terms, within everyday life, it is not problematic to say, I weigh 70 kilograms when stepping on a scale, given that we all share that linguistic convention. However, when turning to a more technical or scientific explanation, one underlines that what that number measures is actually the force that the planet exerts on us, a force contingent on that planet's gravitational strength. Put from another perspective, if someone weighs 70 kilograms on Earth, their mass is 70 kilograms as a stable figure describing the amount of matter, and the weight measured in newtons is around 700, since one multiplies mass by the acceleration of gravity, about 9.8 meters per second squared on Earth. On the Moon, that same mass of 70 kilograms would stay identical, but the weight, if expressed in newtons on the lunar surface, would be far lower. Hence, mass remains a stable quantity that does not change whether you are on Earth, the Moon, or Mars, whereas weight, the effect of gravity, changes along with the environment. That is why, for an engineer designing a spaceship or planning a mission, what matters is the mass of the payload, because it defines inertia and the amount of fuel needed to move it, regardless of how large or small its weight might be on Earth or elsewhere. Another good example, in certain sports with categories assigned by weight, the participants are actually being assessed by their mass, even though it is historically called weight. The scale used on Earth is referencing the gravitational force for classification, but in real terms, the reason it matters is that the mass is what influences performance and strength. If the same competitor were on a celestial body with less gravity, the scale reading would be smaller, though their mass as a competitor remains the same. Sometimes the example becomes even clearer if one imagines an elevator in freefall. Inside that elevator, one would appear to weigh nothing, as though no force were pressing down, even though the mass of the person has not vanished at all. It is simply that the contact force from the floor of the elevator is zero, since both person and elevator are descending at the same rate. Hence, one perceives a lack of weight. However, mass is still absolutely there, so if the elevator suddenly collided with something, the inertia of the person would definitely come into play. Thus, this section teaches us how the mass of an object or individual is separate from the weight, the local gravitational force. A person might measure a certain weight on Earth using a scale, but that is only a local reading reflecting Earth's specific pull. If we traveled to a place with half the gravitational pull, we would find that the scale reading halves, while our physical composition, the mass, remains absolutely consistent. This is precisely why we avoid claiming in strict physical talk that someone weighs X kilograms if we want to emphasize that the quantity of matter remains the same on Earth and on the Moon. Rather, we clarify that the mass is X kilograms and the weight is a separate force measure that changes with gravity. Finally, understanding this difference clarifies many puzzling situations. For instance, it helps to see why your weight is different in an elevator accelerating upward or downward, yet your total amount of matter does not fluctuate. We call that ephemeral difference in scale reading weight variation, but the mass has stayed the same. Therefore, mass is measured in kilograms as a stable value of matter, while weight is measured in newtons if we follow the International System of Units. Although outside of the strict scientific environment, we persist in reading the scale's output in kilograms, aware that it is an agreed simplification. That distinction is enough to prevent confusion when traveling to other celestial bodies or analyzing dynamic movements here on Earth. Centrifugal force and acceleration. There is a frequent misunderstanding in common views of physics which arises from not distinguishing clearly between velocity and acceleration, as well as from misinterpreting what is often called centrifugal force. To begin with, remember that velocity is nothing more than the rate at which an object's position changes over time, while acceleration is the change in that velocity, whether in its magnitude, how fast it is, or in its direction, where it is headed. Sometimes people assume that if an object is moving at a constant speed, there is no acceleration, ignoring the fact that turning a corner or changing direction already constitutes a form of acceleration. For example, a car traveling on the highway at 100 kilometers per hour while maintaining that speed in a straight line does not exhibit acceleration in terms of speed. However, if it enters a curve without altering the speedometer reading, a change in the direction of motion is taking place, which physics considers acceleration, in this case, centripetal acceleration. The speed may still be 100 kilometers per hour, but with its direction shifting, there is a vector of acceleration pointing toward the center of the curve. That detail is essential to understanding why we feel pushed outward when taking a turn. In reality, inertia tends to keep the car, and us, on the former straight path, whereas the route now demands a turn. That feeling is commonly described in everyday speech as "the curve is throwing me outward," bringing us to the following myth, so-called centrifugal force. People tend to believe that when we spin quickly in a car or swing an object tied to a cord, a force is pushing us away from the center of the trajectory. It is popularly known as centrifugal force. Physics, on the other hand, states that no real force pulls outward. What does exist is a centripetal force, the genuine force applied, for instance, by the tension of a rope or by the friction of tires on the road, that compels the object into circular motion. According to Newton's second law, the acceleration points toward the center of the curve, so there has to be a net force in that inward direction. The centrifugal force is nothing but our sensation of inertia. If that centripetal force did not exist, we would continue in a straight path. Because the real force confines us to a curve, we subjectively sense that we are being flung in the opposite direction, as if something were throwing us outward. To illustrate it with practical examples, think of a driver taking a tight curve at a relatively high speed and feeling their body shift toward the side of the car. The driver might believe something is pushing them to the door, commonly labeled centrifugal force. Yet, from a physics standpoint, what is happening is that the car, through the friction of its tires on the pavement, applies the centripetal force that bends its path around the curve, and your body, through inertia, wants to maintain the former straight line. Without a seatbelt or some restraint, you would simply slide, not because a force pushes you outward, but rather because you tend to follow the straight trajectory. Another example, when you twirl a stone attached to a string, your hand provides the inward force, tension. If that tension disappears, the stone flies off in a straight line, yet people commonly say, "Watch out for the centrifugal force that flings it outward." The truth is that the rope supplies the centripetal force holding the stone in a circular path, and there is no outward centrifugal force acting on it. Why does confusion arise? Mainly because our subjective experience is that of being hurled outward, so we conclude there must be a force expelling us from the center. But physics sees that experience as inertia. Without the inward or centripetal force, we would remain in a straight path. Introducing the centripetal force bends us, and we notice the difference between our prior inertia and the car or rope that forces us into a circular path. In non-inertial reference frames, for instance inside the turning car, where we treat the car as our frame of reference, one can introduce the so-called centrifugal force as a fictitious force to explain the feeling. However, it is not an actual force exerted by something external, merely a mathematical device used in an accelerating coordinate system. From a practical angle, grasping the difference between acceleration and velocity, as well as the non-existence of a genuine centrifugal force, prevents certain interpretation errors. If someone asks, "Why does the curve push me outward?" the physics-based answer is, the curve does not push you outward, it is your inertia trying to keep you going straight, while the centripetal force from the car, through the tires and steering, diverts you toward the center of the curve. Understanding that can be helpful, for example, in driving with more awareness of the force that compels you to turn, or in recognizing why objects in rotation need tension or an internal hold to avoid flying in a straight path. In short, acceleration is not limited to speeding up or slowing down. It also covers changes in direction, and that so-called centrifugal force we feel when turning is not a real outward force, but the effect of inertia within a system departing from straight, uniform motion. Taking this concept in its simplest form frees us from the idea that something is physically pushing us out of a curve, clarifying which forces truly act and why we move as we do when following circular or curvilinear trajectories. Energy and the idea of destroying it. A frequently encountered misconception in the study of physics arises whenever people speak of consuming or spending energy as though it might disappear entirely during the process. It is quite common to hear phrases such as, "the energy is finished," creating the impression that energy has been utterly wiped out. However, the law of conservation of energy, one of the fundamental pillars of physics, states clearly that energy is never created nor destroyed, but simply changes its form. When something is consumed, what actually happens is that the initial energy transforms into light, heat, motion, or other manifestations without being annihilated. To illustrate this, consider an ordinary light bulb at home. When you switch it on, electrical energy flows into the filament, causing it to heat up and emit light. At a casual glance, someone might say, the electrical energy was used up. But from a physics standpoint, that electrical energy mostly converted into light and heat. There has been no loss of energy into oblivion, but rather a shift or transfer in how it appears. Eventually, that energy disperses into the environment as radiation and increased temperature. It is no longer present in the form of electrical current in a wire, so it seems gone, yet it has essentially taken another form that is more difficult to reconvert into something we can reuse effectively. The mistake arises when we think if we have spent the energy, it has vanished. More accurately, one could say what has disappeared is the usefulness that energy had in its prior form, because reclaiming it from its dispersed state is complicated or unfeasible. For instance, the heat emitted by that bulb does not spontaneously return to electrical energy. It would require elaborate steps or technology to re-harness it, making such recovery impractical in everyday contexts. This leads to the impression of energy being destroyed, even though in fundamental terms the total quantity of energy in the universe remains the same. The ratio that remains in a concentrated advantageous form, for example the electricity that travels through cables, has simply migrated into a more scattered form, like the heat radiated into a room. One way to see this in everyday life is to note how often we say the battery is spent, implying that the energy is no longer there. In reality, that battery has supplied its chemical energy to power a device, converting part into light, sound, heat, or other outputs. The chemical energy has not ceased to exist, it has changed into those varied forms. The law of conservation of energy tells us that if we tallied up all the energy at the end, heat released, emitted radiation, the generated motion and so on, we would still find the same total as at the beginning, though now distributed in a manner less suited for immediate reuse. In daily life, this distinction clarifies many phenomena. Often, when we speak of energy loss in a system, it simply indicates that the energy has dissipated as heat or that its original concentrated form has become something unexploitable. Not that it was truly destroyed. Consider an automobile which obtains its chemical energy from fuel, then converts it into wheel motion, heat in the engine, expelled gases, and a small fraction of sound. The energy that goes into heat or noise is not erased, but it is no longer available to keep propelling the car. From an engineering or energy economics perspective, this law underpins the quest for efficiency. Designers look for machines and processes that channel the largest share of initial energy into the intended function, like motion in a car, with minimal conversion into heat or noise. Still, achieving 100% efficiency is impossible, and that limitation leads to the real-world outcome that energy appears to vanish when, in truth, it ends up scattered in forms we cannot readily reconvert into something helpful. In conclusion, the law of conservation of energy teaches us that everything used up does not cease to exist. It merely shifts from a more concentrated or practical form to one that is more diffuse or less serviceable. Beneath statements such as the energy was completely destroyed or it was consumed entirely, there is in fact the transformation of energy into heat, radiation, motion, and so forth, but not a true disappearance. Recognizing this helps us grasp why, although light bulbs heat up and batteries become depleted, the total energy in the universe endures. Thus, we need not envision something literally disappearing. Instead, it becomes transferred into other modes that are harder to reclaim, yet remain present. Heat versus temperature. In everyday language, it is quite common to refer to something very hot by saying that it has a lot of heat, or to treat temperature and heat as though they were essentially the same notion. However, in the formal study of thermal physics, each of these words describes a rather different aspect. Temperature indicates the internal state of a body with respect to how quickly, on average, its particles move or vibrate, while heat specifically refers to the transfer of thermal energy from one location or body to another. Although there is a close relationship between these phenomena, confusing them can lead to misunderstandings both in day-to-day explanations and in the comprehension of natural processes. To begin, let us think about the meaning of temperature. When we say an object has a high temperature, we mean that the average kinetic energy of its atoms or molecules is high. If we were to observe it on a microscopic scale, we would see that its particles move or vibrate vigorously. Conversely, an object at a low temperature has particles which, on average, move or vibrate more slowly. This description helps explain why a metal may glow red hot or why the air on a summer day feels so warm. In both cases, temperature denotes that the internal microscopic agitation is intense, even though it may not necessarily imply an enormous total amount of energy within that body. On the other hand, the term heat does not represent the object's inherent property by itself, but rather the process of thermal energy transfer. Heat moves from a region of higher temperature to one of lower temperature, continuing that flow until both equalize their temperatures. One might say, I am receiving heat, or I am losing heat, if energy travels from one body to another, but there is no sense in calling an object a container of heat. Indeed, heat is not a static feature. It is an exchange that takes place when temperature differences exist. Furthermore, how much heat flows depends not only on temperature difference, but also on factors like the body's mass and its specific heat capacity, which influences how easily it gains or loses thermal energy. A typical confusion emerges in statements like, that object has a lot of heat, when, strictly speaking, we observe that it is at a high temperature, not that it contains an abundance of heat. To emphasize the distinction, let us consider the following. A very small object glowing red hot may show an extremely high temperature, yet not harbor a great total quantity of thermal energy when compared to, say, a large tank of lukewarm water. Although that glowing object's temperature might far surpass the water's, if we assess the total energy, the quantity that would be released if it cooled completely, the tank's volume and higher overall capacity might store a larger sum of energy, even though its temperature is more moderate. Put another way, the intense feeling of heat from a tiny glowing object arises from its high temperature and the swift manner in which it can cause a burn upon contact, but the amount of energy it can actually transfer is quite modest in comparison to what a more voluminous, if cooler, body could deliver. Another practical example is how people tend to say, I have a lot of fever, so I have a lot of heat in my body. In reality, a fever reflects that one's body temperature has risen above the usual level, indicating a deviation in the normal range of internal molecular motion. However, that does not necessarily point to an enormous quantity of energy in some absolute sense. The person feels an increased warmth because the difference between their body temperature and the surroundings may be greater, and because the body reconfigures its thermal set point. Yet, it is inaccurate to assume that fever implies a gigantic amount of heat in the sense of total stored energy. Rather, it is an increase on the thermometer scale. The temperature is higher, not necessarily that the body's entire energy content is huge by itself. In daily speech, mentioning heat when we perceive an object to be very hot does not generally lead to practical problems, as people know what is intended. However, in teaching or explaining thermal phenomena in more detail, conflating them can cause confusion if one wants to clarify what really happens when a body warms another, or why certain materials retain heat while others lose it rapidly. The distinction shows that temperature is an intensive property. It depends on the average motion of the particles, whereas heat is the flow of thermal energy from higher temperature to lower temperature. That knowledge explains, for instance, that an object can have a very high temperature yet contain relatively little total energy if its mass is small, or that a more voluminous object at a lower temperature might have far more total stored energy. To see its everyday importance, let us consider the kitchen. The temperature of an oven might be set to 200 degrees Celsius, but whether it is a small oven or a large industrial one can greatly affect how much energy it holds and can transfer to the food. Both ovens might show the same temperature reading, yet one that is larger and has walls with a higher heat capacity can hold on to and share more energy, thus better able to cook larger items. Conversely, the smaller oven may have the exact same temperature, but less capacity to heat a very large mass of food, even though the thermostat's reading is identical. Yet another area of confusion appears when people say an object lost heat in the sense of its temperature went down, or vice versa. Cooling a body does indeed mean that its microscopic molecular agitation has decreased and part of that energy has traveled elsewhere, but does not indicate that the energy vanished from the universe. Rather, it has left that body and gone to another system, consistent with the law of conservation of energy, which says energy merely changes form or place. Thus, a falling temperature means there is less microscopic motion within that object, but the heat that left it is now in the surroundings, raising their energy or dispersing if not contained. We also see these distinctions in how each quantity is measured. Temperature is commonly measured in degrees Celsius, degrees Kelvin, or degrees Fahrenheit, whereas heat is measured in energy units, such as joules in the international system, focusing on the transferred amount of thermal energy. A radiator could be at, for example, 60 degrees Celsius, but the heat it actually supplies depends on how large it is, how long it emits energy, and how big the temperature difference is with its environment, among other factors. So even if two radiators share the same temperature reading, one with a larger mass and higher power might deliver more total energy to the room. Hence, understanding that temperature refers to the average particle agitation and that heat refers to the transfer of energy explains why a tiny object at a high temperature does not necessarily contain more heat than a bigger one at a somewhat lower temperature. Likewise, we recognize that a large volume of water at a mild temperature can store significantly more energy than a minuscule ultra-hot object, and thereby release more energy over a longer interval. That breaks the simplistic idea that only how hot it feels to the touch matters. These contrasts also resolve confusion about thermal sensation, which depends on how skin and nerves interpret the energy exchange. If we say this burns, we mean the object's temperature is much higher than ours, so it transfers energy swiftly to our skin, potentially causing damage if the difference is considerable and contact lasts long enough. But it burns does not mean it holds an absolute heat, but rather that there is a sharp mismatch in temperature leading to a rapid flow of energy into our tissues. Meanwhile, if another source is at the same temperature but has less capacity or mass, it might not produce the same effect or the same level of harm in the same time frame. Finally, it is vital to stress that temperature is an intensive attribute tied to the average motion of particles, whereas heat is an energy flow from a body at higher temperature to one at lower temperature until equilibrium is reached. This helps us recognize numerous phenomena from a person's fever, which is an internal temperature rise, not a giant excess of energy in some absolute sense, to the reason a modestly warm but large reservoir can store more total thermal energy than a small item at extreme temperature. With that approach, physics keeps the concepts of heat and temperature separate in order to detail how thermal energy is transferred and how the internal motion of particles is measured in a given object. Electricity, current versus tension. Among the most frequent misunderstandings concerning electricity is the confusion between what we call current, sometimes labeled amperage, and what we call tension, often referred to as voltage. Although in ordinary conversation these terms are used without much distinction, in physics and electrical engineering they describe very different properties of circuits. Many people see a certain number of volts on a socket and think the higher the voltage, the greater the force or amount of energy that circulates, which is not always correct unless we also take into account the role of resistance and the concept of current itself. To grasp this difference, a helpful image is to compare the system to a network of pipes containing a fluid. In this analogy, tension, or voltage, is comparable to the pressure driving the fluid, while current, or amperage, corresponds to the quantity of fluid that moves through the pipe over time. High pressure alone does not guarantee a large amount of water flow if, for instance, the pipe is narrow or if there is significant resistance. Moving this idea into an electrical circuit, voltage represents the electric potential difference between 2 points, whereas current is how much electric charge travels through the conductor in a given interval. With that illustration, one breaks the myth that more volts automatically means more current. Why do people so often confuse these terms? It is typical to assume if there is a very high voltage, then the electricity is very intense, which does not hold true if we have not considered the circuit's resistance or impedance. A wire at high voltage does not necessarily conduct a large current if, for example, the circuit is broken or the resistance is extremely large. Likewise, an electronic device might be designed to need a certain supply voltage, for instance 12 volts, but the eventual current that flows depends on the device's internal resistance or impedance. If the resistance is high, the current will be low, even though the supply is at 12 volts. We can imagine a practical case. Let us assume we have a power source providing 10 volts and we want to illuminate a light bulb. If the bulb has high resistance, for instance a very thin filament or a design for low power consumption, the flow of current will not be large. If we place an ammeter in series, it might show a modest reading, demonstrating that, in spite of 10 volts being available, the bulb does not allow that much electric charge to pass per second. Conversely, if we have that same 10 volts feeding a low-resistance bulb, the current could multiply as long as the cables and the rest of the circuit can handle that flow without overheating or creating a short circuit. This makes evident the classic mistake of thinking more volts automatically equals more current. The truth is that current depends, following Ohm's law, on the ratio of voltage to resistance. Current equals tension divided by resistance for linear components in a simple circuit. When we say current, we refer to the amount of electric charge that crosses a section of conductor within a certain period, measured in amperes. The word tension, or voltage, is about the difference of electrical potential, that is, how much pressure exists to drive electrons along the conductor, measured in volts. Each of these values describes a different facet of a circuit and should not be confused with the other. One describes the push, the other the flow. Similarly, in the imaginary pipe, pressure is distinct from the volume of water per unit time. There may be high pressure with minimal water flow if the pipe is very narrow or a valve is closed, and one might also have significant flow in a wide pipe if the pressure is sufficient but not necessarily extreme. Nevertheless, it is typical to hear someone say, "I have a high amperage phone charger, so it provides more power," or "This device runs at such and such volts, meaning it is more powerful." Yet power is defined as the product of voltage times current, not just one of them in isolation. A device may need a high voltage but very little current, or the reverse. One daily example is certain electronic appliances that require a high supply voltage but only consume a small current, maybe some milliamperes, while others work at a lower voltage but draw more amperes based on their internal resistance and the intended function of the device. These distinctions are crucial to avoid making errors when handling electrical devices, designing circuits, or merely understanding why some phone chargers have outputs of 5 volts at 2 amperes, while others operate at 9 or 12 volts with different currents, depending on quick charge technology or on cable and device resistance. Grasping that current depends on resistance, and the applied voltage spares us the oversimplification of "if I have many volts, I will have a large current," and clarifies that the resulting current is subject to how much opposition, or impedance, the electrons encounter. In practice, one also notices this confusion in questions such as why a device made for 220 volts in one country does not work correctly in another with 110 volts. if it has not been properly adapted for that different voltage, or if no suitable conversion is performed? Or why a device that aims to function at low voltage with high current needs thicker cables to handle the large flow of amperes, whereas another machine operating at high voltage may draw a lesser current and thus may use thinner cables, assuming similar levels of power? In that way, each of these terms, current, tension and resistance, reflects a particular aspect of the circuit. They converge in Ohm's law and in the definition of power in order to describe electrical behavior. Ultimately, avoiding the erroneous fusion of voltage and current is not only a nuance of abstract physics, but also a fundamental principle for electrical engineering and household safety. Knowing that voltage is the electrical pressure and current is the electron flow helps us see why, under the same potential difference, current will not be identical if the materials, components or wiring differ, and why one device might react differently in a circuit with higher or lower resistance. In everyday life, and in the appliances we use constantly, everything becomes less mysterious once we master these basic distinctions, and we stop believing that more voltage necessarily equates to more current. Thus, physics illuminates how electric energy flows and allows us to better understand the values and magnitudes that appear on transformers, power supplies, or electronics manuals. Light, wave versus particle. One of the most intriguing, yet frequently misunderstood concepts in modern physics is the so-called wave-particle duality of light. It is often said that sometimes light behaves like a wave and sometimes like a particle, which can sound contradictory or unstable. But what quantum theory proposes is subtler. Understood as electromagnetic radiation, light has a description that simultaneously incorporates features typical of waves as well as attributes characteristic of particles, without implying that it is strictly a wave in some cases or strictly a particle in others. A better statement is that light consists of light quanta, called photons, whose manifestations can show an undulatory aspect or a corpuscular one, depending on the experiment and on what variables are measured. To appreciate where this duality comes from, let us revisit the early 20th century, when certain phenomena did not fit the exclusively wave-based idea of light, whereas others did not align with the notion that it could be a standard particle. For instance, diffraction and interference were strong evidence of wave behavior. Light can spread out into interference fringes, much like water waves on a surface. A laser beam passing through a double slit yields a pattern of alternating bright and dark bands, precisely the hallmark of wave superposition. When crests coincide, they amplify, and when a crest meets a trough, they cancel. This phenomenon is elegantly explained if we treat light as a wave that can interfere with itself. Yet a purely wave-based model was insufficient for explaining, among other things, the photoelectric effect, which shows how light can free electrons from certain metallic surfaces when it shines on them. There, the luminous energy appears to arrive in discrete packages, called photons, so that an electron is only ejected if the light has the right frequency, or energy, per photon. No electrons are released if the frequency lies below a threshold, regardless of how intense the beam may be. This discovery fueled the idea that light also possesses a particle-like aspect, meaning it behaves like a flow of energetic little packets that are absorbed or emitted on an individual basis. Here we arrive at the notion of light as a particle. A common misunderstanding is to believe that being both wave and particle is contradictory, or that light switches from wave to particle depending on circumstances. In fact, quantum theory integrates both descriptions within one framework. Light is made up of photons, which are quanta, displaying wave properties like interference, and corpuscular properties like localized energy absorption simultaneously. Thus, it is not that some days light decides to be a wave and other days it decides to be a particle, but that the experiment and the variable we measure reveal certain features. Without these being at odds, it is the richness of quantum nature that allows both. A practical example of wave-like behavior is the mentioned diffraction, or the interference of light in a diffraction grating, where one observes a regular pattern of maxima and minima. These fringes are nicely explained by a wave model, crests and troughs adding or cancelling. Conversely, to account for how light can eject electrons on a metal plate, the photoelectric effect, or how it excites an atom in discrete increments, we describe light in terms of photons. Each photon is or quantum of, electromagnetic energy that is absorbed as a whole. Similarly, the emission of light by certain atoms implies that energy is given off in discrete packets. That quantized nature did not match a purely classical wave model that could, in principle, divide infinitely upon interacting with matter. Confusion arises from the notion that wave and particle are mutually exclusive options. Quantum mechanics, however, supplies a formalism in which photons are entities whose equations exhibit wave-like interference patterns and discrete particle-like interactions. The electromagnetic field, described quantum mechanically, is quantized into photons. Still, photons can produce interference in a double-slit experiment, while at the same time being registered as localized collisions in individual detections. The contradiction only appears if one clings to classical categories. We traditionally imagine waves as distributed phenomena, like ripples on a pond, and particles as concentrated, localized entities. But quantum physics tells us that light, just like electrons and other quanta, holds a so-called wave-particle duality, revealed differently depending on how we observe it. A further misunderstanding often lies in thinking there is a moment when light switches its nature. Light is always photonic, but in certain experiments we witness its wave-related interference, and in others we focus on the discrete absorption or emission events that suggest a particle-like aspect. Quantum mechanics does not present a logical conflict. What classical terms label wave or particle are partial analogies. In reality, the photon has its own quantum description, and the wave or particle labels are different facets of the same underlying entity, determined by the kind of measurement performed. Connecting this to everyday language, it is normal to speak of a beam of light as though it were a physical ray, and simultaneously refer to light waves in contexts of diffraction or phenomena like rainbows and refraction. Neither approach is wrong so long as we understand that light has a dual character, and that speaking of wave or particle is merely a conceptual approach. Thus, there is no contradiction in saying that light can refract and generate color spectra, wave-like, and that it can also be absorbed in discrete energy packets, quantum-like. In simpler terms, the usual error is to think that light must be a wave or a particle in the old-fashioned exclusive sense. In quantum theory, we prefer to describe light in terms of photons, which are quantized excitations of the electromagnetic field and exhibit the properties that classic wave or particle models cannot individually fully account for. It is not that there is contradiction, but that classical theory alone cannot describe the microscopic reality requiring the quantum perspective. Remembering this allows us to see why in a double-slit experiment, even when photons pass one by one, they form an interference pattern, wave property, and yet each photon lands as a localized detection, particle property. In colloquial usage, bearing in mind that light does not turn itself from wave to particle, spares us from believing there is some unsolvable debate over whether it is wave or particle. Meanwhile, science supports the synthesis. It is a quantum of the electromagnetic field, able to interfere with itself while also presenting localized interactions with matter. The vacuum is not nothing. In everyday life, people tend to use the word vacuum to describe a space where nothing exists at all, a drawer with no objects, a room without furniture, a container from which air has been removed. However, in modern physics, the notion of a vacuum spans much more than simply the absence of matter. Referring to a vacuum in a scientific context does not equate to absolutely nothing, but rather a region devoid of significant matter, or containing an extremely low density of it, yet which can still possess remarkable properties and exhibit background quantum phenomena. To understand how this idea arises, imagine extracting that all the air from a container to achieve the lowest possible pressure. Even so, that interior is not in a state of absolute emptiness. There are quantum fluctuations, virtual particles that can pop in and out of existence, residual electromagnetic fields, and in some cases background radiation. Quantum mechanics tells us that even if every stable particle were removed, zero-point energy remains within the quantum fields. This means that a vacuum is not devoid of physical effects, but in fact behaves as a state with definable properties. Perhaps the most striking example is the vacuum of interstellar or interplanetary space. We tend to think of outer space as a completely desolate place, with neither molecules nor anything else. Yet in reality, even those seemingly empty regions contain cosmic radiation, some scattered atoms or the so-called microwave background radiation from the Big Bang that pervades the universe. Although the density of matter may be extremely low, we cannot say there is absolutely nothing. Underlying structure still exists that, for example, enables light to travel across that region. Quantum field theory posits that a vacuum is not a mere nothing, but a fundamental energy state where virtual particles may emerge. This perspective contradicts the everyday intuition of vacuum as a void containing literally nothing. From a physics standpoint, one speaks of vacuum to mean that no real particles of significant density are present at that moment, but quantum fields are still there. Space-time retains its characteristics, and the possibility remains to create or annihilate particles in that substrate. An illustrative example is the Casimir effect, where two closely spaced metal plates experience a force attributed to the electromagnetic field fluctuations in what we call vacuum. Why do we casually say something is empty without further nuance? From a practical standpoint, if we open a drawer with no objects inside, we say the drawer is empty. On a macroscopic scale, that phrase suffices to convey that nothing useful or visible is contained. But were we to be very strict, there could still be air inside, photons, ambient radiation and so forth, which from a human perspective may not be perceptible, yet from a physics perspective is not utter nothingness. Similarly, when science fiction depicts outer space as an inhospitable realm where there is nothing, it is an oversimplification. In truth, even the vacuum of space can contain particles at extremely low density, extended fields, and background radiation throughout the cosmos. Additionally, the notion of a vacuum in physics is intertwined with the possibility that, for instance, pairs of virtual particles and antiparticles can appear. Even if their existence is momentary, it is part of the quantum structure of what we regard as empty. Some have even speculated about harnessing energy from that state, although thermodynamics and quantum mechanics indicate it is neither simple nor infinitely exploitable. The main point is to recognize that a vacuum has measurable characteristics: its electric permittivity, its magnetic permeability, the speed of light, defined in a vacuum, and the presence of field fluctuations. These traits distance it considerably from the notion of nothing. A further example is the propagation of electromagnetic waves. We say, light travels through a vacuum. If that vacuum were genuinely the complete absence of everything, it would be hard to explain how that empty space can serve as the medium in which an electromagnetic wave moves. Historically, people hypothesized an ether to fill that vacuum, but ultimately abandoned the idea in favor of a field-based approach that does not require a material substrate. Yet this does not imply that the vacuum is nothing. It means the electromagnetic field propagates, and vacuum is viewed as the state where no real photons are present, even though the underlying quantum field structure remains with which the wave can interact. When we bring all this back to everyday thinking, we see that if an astronaut in Earth orbit looks around and says, "There is only vacuum," from a practical perspective, yes, the number of atoms or visible matter is extremely small, no clouds, no obvious matter close by. Even so, that astronaut is immersed in solar radiation, cosmic rays, Earth's gravitational field, and the cosmic microwave background. Indeed, the density of matter is minuscule compared to Earth's surface environment, but absolute zero is not reached in matter or energy. Hence, physics uses the word vacuum to mean the absence of real particles, or a region without substantial matter, rather than utter emptiness. Quantum mechanics points to the fact that even in that state, field fluctuations, quantum vacuum processes, and the possibility of virtual particle generation remain. This was one of the major findings of 20th century physics. The vacuum is not absolute nothingness, but encloses properties that can manifest in multiple ways. If we were to equate vacuum with nothing, the history of science itself goes well beyond that simplistic vision. Fields and background energy create an environment more complex than the word vacuum might suggest to an ordinary ear. Perhaps in practice, a room at minimal pressure with no visible objects suffices for us to say it is empty, but physics would note that there is always something inside, be it electromagnetic radiation, faint traces of air, or field fluctuations. Absolute nothingness is never attained. Understanding this discards the error of assuming that a space lacking apparent matter must be the total negation of something, so it becomes more accurate to speak of the vacuum as a state with extremely low matter density and the inescapable presence of fundamental fields and residual energy. With that, we learn that when we look out at outer space, we should not view it as a void where absolutely nothing exists, but as a realm where, though the density of matter is vanishingly small, forces and energy are still present. The electromagnetic field, gravity, quantum fluctuations, these all inhabit that vacuum which is not synonymous with nothing. In this way, we arrive at a deeper method of seeing reality and abandon the oversimplification that, in physics, vacuum equates to plain absence. What appears to be a lifeless void retains properties capable of sustaining light propagation, field effects, and quantum events, even though our intuition may have historically labeled it total emptiness. Gravity is not suction. In everyday conversations about how gravity keeps us on the ground, one often hears someone say that Earth sucks us in or pulls us like a magnet from its center. While this image can serve as a casual metaphor, it can also lead to the erroneous notion of some kind of vacuum pump in the planet's interior that draws us downward. Neither Newton's theory nor Einstein's general relativity supports the idea of a suction force. In Newton's framework, gravity is an attractive force acting at a distance, causing Earth's mass and our own mass to pull each other. In Einstein's relativistic view, gravity arises from the curvature of space-time around massive bodies. None of that suggests Earth operates as a vacuum that sucks us in from its core. To understand it better, let us recall that, according to Newton's law of universal gravitation, two masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This means we likewise exert a force on Earth, though our personal mass is quite small compared to the planet's, and thus the effect is essentially noticeable in our own body. Newton described that force as a mutual pull without referencing suction. There is no empty space inside Earth that pulls people in. It is a phenomenon of mutual attraction based on mass. In general relativity, the explanation takes a more geometric approach. The presence of mass, or energy, deforms space-time, and objects move along trajectories that, in the absence of other forces, follow what are called geodesics in this curved space-time. When we say something falls to Earth, the real meaning is that space-time curvature directs it closer to the planet. From an external observer's perspective, it looks like there is an attractive force, but it is not a suction, as if something were vacuuming the object up. Rather, it is the outcome of how space-time is shaped and how the object's path is deflected to that shape. Why, then, do so many people talk as though there is a vacuum pump pulling us in? Largely, it stems from our everyday experiences. If an object drops from a treetop, we watch it fall straight to the ground and say, "Earth is pulling it," or "it is sucking it down." But neither the tree is pushing it downward, nor is Earth functioning like an upside-down hose, dragging it along. In Newton's view, gravity is simply a force that points toward Earth's center, specifically the system's center of mass. With nothing to support it, the object accelerates downward because of that attractive interaction. In relativity, the tree and the object follow paths in space-time, and once the object is no longer propped up, the curvature carries it down. There is no notion of a sucking agent in the planet's interior. Another enlightening example comes from comparing with the air we breathe. Where there is a pressure difference, we say air enters because we suck it in, such as with a bellows or a device that lowers internal pressure. That is, in fact, a fluid dynamics phenomenon, the movement of higher pressure fluid into lower pressure. But gravity does not operate that way. It is not that Earth has a lower pressure at its center that pulls us, but rather it is a fundamental interaction between masses. Nor does a pressure gradient account for an apple's fall. The apple is not pushed by any fluid carrying it downward, but subject to gravitational attraction that holds even in a vacuum. It also becomes more obvious that if gravity were suction, one might imagine that inside Earth there is some hollow region drawing us in, which is not the case, nor does that mesh with the fact that the gravitational force depends on mass and distance and extends well beyond the atmosphere. When a satellite orbits thousands of kilometers above, it still feels Earth's gravitational influence, and nothing akin to a central vacuum is pulling it. Instead, the satellite remains in free fall around the planet, and because of its tangential velocity, it avoids hitting Earth but never escapes that universal mass-to-mass interaction. In the relativistic explanation, the image of suction becomes even less fitting. Earth, by virtue of its mass, warps the local geometry of space-time, compelling nearby objects to move in a direction that draws them closer unless they have enough lateral velocity to remain in orbit. This model portrays gravity as a geometric outcome, not a phenomenon of pulling via suction. Hence we see no void in Earth's interior sucking, but rather that the planet's mass and energy distribution shapes how objects follow geodesic lines in space-time. Although phrases like "Earth sucks us in" do not cause big issues in everyday talk, they can overshadow the real mechanism, either a mutual attractive force in Newton's sense or a curvature of space-time in Einstein's. Understanding this can clarify, for instance, why objects of different masses fall at the same speed if air resistance is absent, or why an astronaut in orbit is not being sucked in by Earth, but rather traveling on a continuous fall whose horizontal speed yields an orbit. Many apparently simple notions like falling down or going up become richer when we realize there is not a vacuum-based pump at Earth's center, but a global effect that acts on all massive bodies. This is evident when an object rolls down an inclined plane. It is not some hidden empty space pulling it downward, but the force of gravity at each point, always directed toward Earth's center of mass, while the plane merely redirects part of that force to support the object and let it roll downhill. So there is no need to imagine an invisible suction line. The explanation fits perfectly with gravitational laws or general relativity if one seeks deeper understanding. In short, the best way to discard the mental picture of suction is by noting that gravity exists even in vacuum, where there is nothing that could be pulling in that manner. It is a fundamental interaction causing masses to attract, or a geometry that forces bodies to follow paths that converge them. Beneath the word gravity, one does not uncover a giant pumping mechanism inside Earth, but a property of the universe dictating the fall of apples and the orbits of planets. Newton's and Einstein's viewpoints diverge in how they interpret that phenomenon, distant force or space-time curvature, but neither proposes a suction apparatus. What we notice when dropping out of a tree is the manifestation of that attraction or that geometry without needing tubes or inner vacuums pulling us to the center. The expansion of the universe is not taking place. Among the most widely spread yet confusing ideas about the cosmos is the belief that the universe expands outward as if there were a larger space into which it inflates, much like a balloon in a room. In people's minds, one envisions galaxies receding in some pre-existing immense void that surrounds our universe. Current cosmology, however, indicates there is no outside in which the universe grows. Rather, space itself is expanding in all directions, increasing the distance between faraway objects without relying on a bigger external container. To unravel this notion, we often resort to the balloon analogy. Imagine a balloon on whose surface we have drawn several dots representing galaxies. As the balloon inflates, each dot moves away from every other one, not because they travel outward in reference to an edge, but because the surface of the balloon stretches. If one measures the distance between two dots, it increases, yet each galaxy is not traveling on its own. It is the curvature and expansion of the surface that is growing. One of the most important elements in this metaphor is understanding that there is no single center on the balloon's surface from which expansion originates. Likewise, our universe does not have a privileged center. Expansion takes place everywhere simultaneously. The error of believing that the universe expands into some beyond arises partly from our human tendency to imagine any expansion like a balloon in a room, where the balloon indeed inflates within a greater three-dimensional space. But contemporary cosmology affirms that the universe, when considering space-time, does not require an outside. It is space itself that is stretching, pushing clusters of galaxies farther from one another over large scales. This may create the impression that the galaxies are receding from us, but in reality, each region of space is growing in all directions, so that viewed from any point, all the other galaxies appear to be moving away. Some ask, if everything expands equally, should not the distance between atoms or the extent of our solar system also grow? However, the expansion of the universe predominantly takes place on very large scales, that is, among galaxies, because local forces, electromagnetic interactions among atoms, gravity in solar systems and galaxies, hold these structures together. The gravitational force prevents, for instance, the solar system from stretching since the sun's pull is strong enough to overshadow cosmic expansion at that smaller scale. The expansion effect emerges when we look at huge distances, encompassing millions of light-years, where the gravity binding distinct galaxies is no longer dominant. The balloon analogy helps to illustrate that there is no boundary or center from which everything is moving away. Inflating the balloon, each dot drawn on its surface sees all the others recede, and if we look for a center of expansion within the surface, we will not find one. Equivalently, in cosmology, there is no single physical center in three-dimensional space from which everything separates. Every part of space behaves as though it is at the center, observing how all galaxies recede. In the Big Bang theory, we do not describe a conventional explosion bursting outward from some point in a larger void, but rather a stage in which everything was denser and hotter in a primordial epoch, and space itself grew over time. This expansion does not require a greater external space, just as, in our two-dimensional balloon illustration, the surface does not need to inflate into something if we treat it as a separate geometry. In three-dimensional reality, distances swell likewise, without a bigger external container surrounding the universe. For those who wonder what lies beyond the universe's expansion, cosmology holds that the question rests on a faulty assumption that there can be a beyond, whereas space-time itself constitutes the totality of cosmological geometry. We are not a balloon in a room, but an entire space that expands upon itself, explaining why observations show that galaxies recede in proportion to their distance. Hubble's law indicates that the farther away a galaxy is, the greater its apparent recession speed, consistent with the stretching of the spatial fabric rather than motion toward an outside. By realizing that the universe does not expand into something like a bubble of soap in the air, we understand that the cosmos in itself stretches, changing the map of distances without needing an external reservoir. The balloon in a room image is just a teaching device. One must remember that on the balloon's surface, meant as a two-dimensional analog, each point separates from the others without a center. It is not that there is some infinite place outside where the universe grows, but rather that, on very large scales, separations increase. This clarifies why astronomers do not find a particular spot that serves as the center of the universe, because in actuality, expansion takes place everywhere at once, and every observer in any galaxy sees the same phenomenon, a panorama of galaxies receding in a global fashion, devoid of edges or limits. The Big Bang was not an explosion of matter. One of the most widely held yet somewhat misleading images of the Big Bang describes it as a gigantic explosion hurling matter in all directions inside a pre-existing void. While this representation is easy to imagine, it strays from the view proposed by modern cosmology. Rather than a sudden blast of matter located somewhere, the Big Bang theory posits that the entire universe, space, time, energy, and matter, was in an extremely hot and dense state, and from there it began to expand. There was no location in which something exploded. Instead, space itself came into being and grew over time, concentrating all matter and energy in that initial phase, and then gradually spreading them out as it cooled. To understand the misconception, it helps to recall the balloon analogy again. Picture a balloon on whose surface we have drawn multiple dots that represent galaxies. There is no single center within the balloon from which the surface, the analog of our universe, expands. Instead, every region of that surface expands uniformly, pushing the dots farther away from one another. Translating that idea to cosmology, we see that in the initial stage, what we call the Big Bang, space was far more compressed, with densities and temperatures that were immense. As time went on, that space grew so that now, billions of years later, clusters of galaxies find themselves at vast distances from each other. The metaphor of a Big Bang explosion in a larger void stems from our experience with terrestrial explosions, but cosmology stresses that there was no external emptiness. Rather, space-time as a whole was in that early, hot, dense condition. This misunderstanding leads people to ask, where did the Big Bang happen, as if it were a localized event in some larger container? In reality, it was not a single point in a pre-existing space. Rather, there was an initial or primordial phase in which the total extent of the universe was concentrated. Every part of the universe took part in that hot, dense state. There was no center, nor an outside. Hence, we cannot say matter exploded outward. It is that space started to expand, carrying along the particles, radiation, and energy that existed in that primeval plasma. What sets it apart from everyday explosions, like a bomb or a volcano, is immense. In normal blasts, there is a focal point where energy is released and the shock wave travels across the environment. Under the Big Bang, the environment itself was everything. There was no inside and outside in the way we usually interpret those words. There was no external medium in which something exploded. The Big Bang is more akin to the simultaneous expansion of all space, which in its earlier state was inconceivably dense and hot by everyday standards. As that space expanded and cooled, it gave rise to conditions suitable for particles, nuclei, atoms, stars, and galaxies. None of it implies a central explosion or an edge upon which matter was thrown. As for what is often called the cosmic microwave background, CMB, that we now see throughout the universe, it is a vestige of that earlier hot, dense phase, perceived as a uniform thermal glow everywhere, reinforcing the idea that everything was uniformly filled with such energy. It did not come from one specific place but emerged across all of space at once, becoming evident a few 100,000 years after the initial phase when the universe cooled enough to become transparent to light. As space stretches, the wavelength of that radiation becomes longer, cooling to its present temperature of about 2.7 Kelvin, an echo of expansion. Stepping away from the metaphor of a big blast at a point can clarify how the universe is structured and the fact that there is no single location or edge from which matter was ejected. The Big Bang did not refer to something that exploded in one spot, but the onset, or extremely early stage, of the expansion of space-time itself, containing all that exists. Every region of the cosmos was part of that dense initial condition, and the entire space has been enlarging ever since, scattering the galaxies like marks on an inflating balloon surface without an outside region that it expands into. This is why, when people ask, what happened before the Big Bang? Cosmology cautions that before and beyond lose their usual meaning if we realize time and space themselves emerged from that initial state. We are not talking about something that blew up in a vacuum. We are talking about the emergence of the conditions at space-time's beginning and how it evolved into what we see today. Understanding that nuance avoids many misconceptions, the Big Bang did not explain how something erupted in a bigger place, but rather how, from a hot and dense phase, the cosmos began to unfold, leading to the current framework, with galaxies receding from one another as space expands. Not because something flung them outward like a shock wave from a normal explosion. Each location in the universe was part of that beginning, so each region bears the imprint of that shared past. There is no physical center, no boundary, no beyond into which matter was deposited. Cosmology underscores that the earliest stage of the universe already included all of space-time in a compact, extreme condition, and that over time it spread out into what explains today's distribution of galaxies, the background radiation, and how matter arranged itself.